or wider and so on, but they're basically all like this. That's how knowledge is stored in your brain. And we want to ask the question, can we understand how this structure works? Because if we understand how it works, then we can build machines that work like it. And the answer is you can. And we have. We figured it out pretty much. There's some things we haven't gotten right yet, but we got 90% right, some large percentage of it. We have the basics of how this works. I'll just tell it to you. It's not that hard to understand. It's actually, I promise, it's pretty simple. It's not trivial, but it's reasonably simple. So the question is, we've come up with a term for this. I call it hierarchical temporal memory. It's a very descriptive term. It's hierarchical memory, and you'll see temporal because it's very much involved in time, how time is stored. Now, we already said that all nodes do the same thing. That's a given premise that comes from the neuroscience. They all do the same thing. What is it they're doing? Well, these are just cells. They're looking at patterns. They don't actually know what the patterns mean. They don't know if it's vision or anything else. They're just patterns. It's all the same. What they do is they do two basic operations, any node in this hierarchy. They look for common spatial patterns, things that occur at the same time, and then they look for sequences of those, things that are typically common follow-on at a time. You can think of it like a melody. A common temporal sequence would be, I hear a series of notes or intervals over and over again. I say, oh, I recognize that. That's a melody. I'm going to remember it. I'm going to remember that sequence. And what I do as a node in this hierarchy is I pass the name of the sequence, the name of the melody to my parent. I don't give them the details. I don't say, here are the notes. I say, here's the name of the melody I recognize. And what happens is the parent's now doing that too, because it's all doing the same thing, and the parent learns sequences of sequences. And you end up with a hierarchy of sequences of sequences of sequences. And one of the consequences is if you have a very fast-changing pattern at the bottom, like my speech right now, going on your cochlea in your ears, creates this very fast-changing pattern on the bottom of your auditory hierarchy in your brain. As it goes up the hierarchy, it slows down. It's basically learning, oh, I recognize this piece, this piece, this piece. And then you have slower changes at the top and faster changes at the bottom. Now, each node also knows statistically what's likely to happen next. It's learned sequences and knows what's likely the next input going to be. And because of that, each node can make predictions. And your brain is constantly making predictions about everything, all the time. You're not even aware of it, but it's constantly making predictions about everything you're going to see, hear, and touch. And what it does is it passes that prediction down the hierarchy. It tells the child, here's what you should be expecting next. Anticipate the following. And so you can take a very high-level pattern at the top of the hierarchy, a stable pattern at the top of the hierarchy, and as you unfold it, it unfolds in sequences and sequences and sequences, and it can create a very complex pattern like my speech, which is what's happening right now. I'm basically creating a very complex, lengthy pattern on my vocal cords, and it's being unfolded sequences in this hierarchy. What you do if you do the training right, if you expose this thing to patterns in the world, it'll learn a model of the world. It learns a hierarchical model of causes. Causes is the term that's used to represent sort of statistical regularity in the world. So it's a hierarchical model of causes in the world. And you can do a lot with that. We use Bayesian techniques, and the brain looks like it uses exactly what Bayesian techniques, the same thing the brain does. But basically, it's like a big belief propagation network. And what this means, if you know it, even if you don't know what that Bayesian stuff is, but basically it means you can put a pattern at the bottom that's very noisy or occluded or missing stuff, and you have one pass through the system, and have a very clear percept of what's going on at the top. Your perception of the world is very clean. If you actually could see the data coming on your senses, it's messy, it's awful. And when researchers start looking at this, they can't believe it works. It's because you have this belief propagation network, and by the time you get to the top, it just cleans it all up. It's like, what's the most common belief here? It makes sense. A friend of mine, a guy was working at my institute, a graduate student named Dilip George. He did this work 3 years ago. So some of you may have seen this before. I apologize. I'll show you some new stuff if you haven't seen this. But 3 years ago, he says, can we build this stuff? And he said, let's try. And so he started off with a very simple vision system. He built a 3-level hierarchy that looked at a 32 by 32 pixel patch. And so at the bottom of this hierarchy, there's 64 nodes, each looking at 4 by 4 pixels and so on. It's a very simple visual system. He trained it on a series of line drawings. These are the 48 characters he used. And when he trains these, you just take these little pictures and we make movies of them. I'm not going to show you that, but we make a movie of them. We move it in front of the retina of this little memory. And it learns sequences of sequences and sequences, and it learns to recognize these things. So we can come back later, and we can now show it novel patterns it's never seen before. These are all patterns that are just noisy, messed up versions of things that it was trained on. So on the left, you see there's each column is a different category. So if we have dogs on the left, you can see the dogs are recognized facing left and right with a lot of noise and distortion and so on. These are very novel patterns. Hasn't seen these. Look at the 6th column over in the fifth row at the bottom there. That's a mug. And you can see that mug has hardly a single straight line or corner. You and I can see the mug there, so can this system. You can download this software from the Memphis website and play with it. It is a lot of fun. You'd be surprised how fun it is, and it's really good. It's very hard to trip it up. And you can like morph between two images, and just when you like really messed up images, and just like you say, I think this is starting to look like another character, it'll do the same thing. Now, this is a trivial problem. I mean, not trivial. It's a toy problem. It's not trivial. It's actually a very hard problem, but it's a toy problem. But we experimented with it a lot. I'll show you something that most of you almost certainly haven't seen. Because the system stores sequences of patterns, it has this memory of time, how things change in time. We can do what's called time-based inference. Time-based inference is essentially saying, inference is just recognizing something, but I want to do it through time. My language requires time-based inference. All auditory input requires it. If you're going to recognize it, it requires you hear it through time. When you touch something, you have to move your hands over it through time. It's time-based inference. Vision is mostly time-based inference. Things are usually moving around in the world, yet we can do spatial inference. We can just flash an image and recognize it. So here's a picture of the little helicopter. You probably can't see it. One of our characters. It's at the bottom of this picture. It's hidden in a field of noise. And I would put this into our system. It does pretty good, actually. It gets about 20% recognition rate. Even though there's a lot of noise in there, it's kind of hidden. But it's not anywhere near 100%, which it should be. We now can show the exact same thing, but we're going to show it a little movie. We're going to show that little image moving through the field of noise, and it'll pop out for you. You'll see it. So watch it. It's a little movie here. And you'll see the helicopter move to the left at the bottom, and then it go across and move across the top. And it sort of pops out for you when it moves like that. Same thing happens for the HTM. It pops out. It does much, much better recognizing that. I said, oh, I got it. I can see it. It just jumps out, just like it does for you. This is something that brains do all the time, but most recognition systems can't do this at all because they don't deal with time. I can even show the same thing where the noise is dynamic. So I'm going to show the exact same movie, but the noise is changing. In this case, pretty much every pixel is changing in every frame of this image. And you'll see, but the helicopter still can pop out, and it does for you, and it does for the HTM. And although the recognition isn't quite as good, it's still much, much better than if it didn't have the noise. So we took we basically did a lot of testing, doing attentional stuff and all kinds of stuff, just to make sure we could really build this stuff. But what do we do with it now? What to do? So this is several years ago, and I said, the first thing I'm going to do is I'm going to write a book about this. And I did. I wrote a book called On Intelligence. It was published 3.5 years ago. It's now available in 16 languages. It's been very well received in both the computer science and the neuroscience communities. I just gave some major talks just last year in the neuroscience world. It sparked a lot of initiatives. In the book, I describe the basics of this theory. I don't describe how to build it technologically, because I didn't know at the time I wrote the book. But I describe it from a biological point of view. And there's various initiatives around the world, people trying to recreate this stuff and build machines that work like this. I just discovered recently there's actually an Iranian group. Believe it or not, I'm not making this up. You can find their Iranian website where they've got an HTM website and they're building this stuff. And of course, we have initiatives in Europe, and there's stuff going on here in the United States as well. The second thing we did is I said, look, I want to accelerate interest in this field. I want to get more people working on this. I want to get more smart people coming on board, and there's a lot to be done. So I said, let's turn it into a technology ourselves. So I was running a nonprofit institute at the time. I moved it lock, stock, and barrel to Berkeley, because there was a bunch of scientists who were employed there. We then formed a company called Numenta about 3 years ago. I formed it with Dilip George, the guy who did that work earlier, plus a couple other people. And we basically are creating a platform for experimenting with these software, these tools, with the hierarchical temporal memories. We had our first release of this software a year ago. We called it pre-alpha because it had many, many limitations to it in the algorithmic side. But it was a very robust system otherwise. And then this year we're coming out with a very vastly improved version of it. I'm not sure what we're going to call it yet, but we've made a huge amount of progress in the last year. And our goal is to build a community of developers, getting a lot of people working on this, it's because there's many, many things that need to be done.